devices you already have in the grid, because they will kind of interact with each other. So often when you are designing a device, you may not have considered the possible interactions with other devices in the grid. Like there can be parallel other kind of chargers, right? There can be different kinds of power electronic devices. So it is important that you, when you are designing your charger, you should also consider like what kind of other devices are there in the grid. Let me give you an interesting example. When renewables first came into operation, so when they initially connected, especially wind turbines in remote area, medium voltage distribution system, so they saw that whenever they are connecting the wind turbines, the voltage is shooting up and eventually it is tripping due to over voltages. So here you can see that as a separate device, as a isolated device, wind turbine generator was designed fine. But the moment it was connected to the grid, the behavior of the grid also impacted, right? The similar way, when you are connecting a electric vehicle charger, you should also consider what can be the possible impact of this on the grid and vice versa. So in this talk, that is uh, something which I will be discussing, mostly from the system's point of view. So if we look at charging types, as we know that mostly from charging power level point of view, you have two kinds of charging, slow charging and fast charging. If we look at slow charging, it's kind of overnight charging. You charge at low power level, so it takes lot of time, and it is more common present day. It is in homes, in public offices, right? So you will see this kind of chargers, right? So it is usually rated lower than the maximum household power, which is 22 kilowatt in European Union and 19 kilowatt in the United States. So this kind of charger takes maybe 8 hours, 9 hours, 10 hours for charging the vehicle. As a result, they are mostly suited for short distance travel, right? So because in the long distance travel your charge is over, you cannot wait for such a long time to charge your vehicle, right? So the main features of this kind of chargers are extending extended charging period, and usually they are installed in wide area. On the contrary, the new concept which is becoming popular is fast charging. Now, why we need fast charging? See, one of the major barrier of EV adoption is the range anxiety, right? If I charge my car, how far I can go? Can I go to 500 kilometers in one day and come back in one charge? If not, then how can I refill my car, right? So these are the things comes to our mind whenever we think of buying an EV, right? And also like what is the convenience of EV recharging? Like in petrol pump, if I go in few minutes I can recharge my car, right? Can we have similar kind of experience if go if I charge my EV? Right. So these are the major thinking which comes to our mind whenever we think of purchasing an EV. Okay. Now, during long distance travel, the charging time should be comparable to the refueling time of conventional vehicles. Obviously, when we are going somewhere, we should want the EV to be charged within few minutes, right? We cannot wait for long time, right? So here comes the role of fast charger. So this is a graph which I have taken from a paper. So it presents the number of daily fast charging events with respect to daily distance traveled, right? So here you can see that for long distance travel you have to do fast charging of your device, of your EV, right? Now when it comes to fast charging, so the maximum acceptable charging time for to the most drivers during traveling is considered to be 15 minutes. That means within 15 minutes you should be able to charge your car fully, right? And if you have such fast charging facility, then you can actually, this kind of charging is suited for both short and long distance travels, right? But you need you because it obviously needs high power, because if you want to charge your car batteries in such a short time, you need to charge it at high power, right? And such a high power you cannot have in your home, right? So usually you need dedicated charging station for this purpose, right? So now charging types classifications, if we see the chargers classification based on IEC 61851-1. So this I'm sure you already know. So mode 1, mode 2, mode 3 and mode 4. So mode 1 and mode 2 basically AC based and it's slow charging. Mode 3 AC and it also supports fast charging, and mode 4 is DC fast charging. Now, if we look at the classification based on SAE J1772, so there are three types of chargers. Level 1, so AC onboard chargers, level 2 AC onboard chargers, and level 3 DC offboard chargers, which is fast charging. Right. So this is a basic statistics of some of the cars and their range and required charging power. So fast charging power. So here you can see that especially for the Tesla cars, you need quite a high powered charging, right? Like Tesla Model 3 has 174 kilowatt, Porsche as 201, Tesla Model S as 228. Okay, so you can see that how much high power charger is required, right, for charging these cars. Now we will discuss. So we are here discussing fast charging in a dedicated charging stations, right? So ideally, these kinds of fast charging stations are best suited to be constructed along routes for long distance trips. It's quite obvious, like people who are going out of town, right, for long distance. So there should be some fast chargers, right? So and usually the power ratings of these fast charging stations can be few megawatt. As an example, Tesla's fast charging station comprises 10 to 12 number of 150 kilowatt DC fast chargers, resulting in a total power capacity of 1.5 to 1.8 megawatt. Okay, this is just one example, and this much high megawatt power you cannot connect to a low voltage distribution system. So usually these fast charging stations should be connected to medium voltage distribution systems. Right. So this is just a uh, conceptual picture to tell you how these fast charging stations will be connected. So from the substation, mostly medium voltage line you will take out, and then you will bring it to the fast charging stations, right? And usually they will be on the routes of your long distance trips. Now this is a schematic diagram of two possible configuration or architecture uh, which you can have in a fast charging station. So in the first in figure, you can see that I am stepping down the medium voltage to low voltage, and then I have two stage inverters, first AC to DC and then DC to DC, right? So here your distribution system is within the fast charging station. Within the station, the distribution is AC, right? Only before that charging, you are converting it to DC, right? And you have obviously energy storage to take care when there is no grid in some scenarios, right? And another alternate here, so here somebody can argue that why you are having so many AC to DC conversion. Instead of that, why can't you have only one conversion, right? And then you have a DC distribution systems. So the second architecture basically talks about uh, such configuration where the distribution within the fast charging station is DC. Correct. And another interesting configuration which people are also considering, that because you can also use your local generation such as wind and solar, right, to consume or to use that for charging your car. So what you may have within the charging station is some amount of solar and wind power, and you consume that power locally for charging your cars, and extra power needed you can bring from the grid. So what are the characteristics of fast charging station? The charging power is high, load demand is centralized because it's a high load at one point in the medium voltage distribution system. So load demand is centralized at the charging station, and mostly the charging is more during daytime because of the long distance travels. And then the load with respect to the distribution system, the load appears to be pulsating in nature, right? Because now you are charging your car for a very short time with high power demand, right? So it basically appears kind of a pulse, not exactly pulse but as a pulsating behavior, right? So it has that way some similarity with the traction or train loads. Okay. So if you look at literature, so unfortunately not much study have been done focusing on the fast charging stations. There are uh, studies which focused on slow charging stations. There are plenty of studies, but fast charging station there are not much study available. Whatever study currently is there, they mostly focus on the power quality aspect. Okay. So next I will mostly discuss the power quality impact by the fast charging stations. Okay. So now power quality impacts can be broadly classified into voltage fluctuations, harmonic stability, and supraharmonic emission in the context of fast charging station. So voltage fluctuations, there are two major criteria or quantity we can say which are used to measure the voltage fluctuation. So one such is rapid voltage change. So as it is defined in IEC standard, rapid voltage change is basically a single rapid variation of the RMS value of a voltage between two consecutive levels which are sustained for a definite but unspecified durations. In a simple word, it's basically the change in RMS values of the voltage in consecutive time period. Okay. This is one indicator of voltage fluctuations, and another thing is flicker. Flicker is basically a visible change. So here comes the vision, like what we see, right? Its impact on our vision. So it's basically a visible change in lamp brightness due to voltage fluctuations. Now a study was done using IEEE 4 bus test feeder. I have taken it from an existing paper, and a vehicle arrival time of this distribution was considered. This distribution was same as your petrol or diesel vehicle, right? The vehicle arrival time was taken to be same as your conventional vehicles, and then 10 charging slots were considered with DC charging, and there was a simulation study to know what are the impacts of these fast charging stations, right? So it was found, so here you can see that it was found that this particular figure is on flicker. So you can see the standard limit is 1.0, and you can see that in many instances it is crossing the standard or specified limit. Okay. So in general, the observation was that rapid rapid voltage change and flicker increase with DC fast charging power. That means if your DC charging power is higher, you have to be more careful about RVC and flicker, because you may cross the limits in these parameters specified by the standard. Then comes the harmonic stability. This is a very important, especially if you are connecting multiple chargers, high power charger within a station. What is harmonic stability? Harmonic stability, in simple words, is the stability of a system in harmonic domain. So whatever harmonic frequencies are expected in that system, in all those frequencies, your system should remain stable. Right. So that's the basic concept of harmonic stability in simple words. Now, the output now in case of inverter, the output impedance of an inverter can behave like a negative resistance at some frequencies, not all, but at some frequencies. So if there is a resonant point in the same frequency zone, then what will happen is the inverter will resonate and there will be instability, right? So this is basically one of the root cause of instability of power electronics based system. So there are many ways a inverter uh, can participate in a harmonic instability phenomena. There can be caused by PLL, they can be caused by your control loops. So this figure is one of the example. So there can be many way of harmonic instability. This figure present one of the way. So here this you can see that the system eventually become harmonically unstable. So this is very important, especially if you are developing a charger and if you are planning to have a fast charging station where 10, 12 such charger will be connected, maybe with a capacitive cable, right? So you should always carry out this harmonic stability study so that to ensure that these chargers do not interact with each other and lead to harmonic instability event. So this is a very important study to be done. Okay. Otherwise, as a system this will not work. Right. So this is something should be carried out. Okay. And the other impact and the last impact, which is also very interesting and also new to the power systems. So if you look at IEEE standard 519, which talks about basically harmonic injections, right? So you will see very interesting thing. They always talk about up to 50th harmonic, and 50th harmonic in a 50 hertz system is 2.5 kilohertz, right? So in conventional power system, usually all harmonic studies are done till 2 kilohertz or 2.5 kilohertz, like that, right? So above that, it is observed that those harmonics are almost non-existent in a power system. So there is not much discussion or not much uh, limits are given for that those frequency range, right? But in presence of power electronics, that is about to change, that is going to change, right? So converters also inject these higher harmonics, like we call it supraharmonics components within the frequency range from 2 to 150 kilowatts. So in simple words, the converters are now injecting very high frequencies also. As a result, if you have, especially in case of fast charger, where you have many parallelly connected fast chargers, right? So they all will inject these high frequencies, right? So now what will be the behavior in presence of these high frequencies, that has to be evaluated. So this is just a figure of supraharmonic emission. Now you may say that your converter does not inject such high frequencies, right? You take care. But the problem is, usually because the standards do not give any particular limits for this range, so there are many products which actually which can inject this amount, this range of higher harmonics, because standards do not specify any limits specifically for this range. Okay. And also the devices are often not immune to disturbances in this frequency range, right? So you have to, when you are designing the DC fast chargers, you have to see that they don't inject higher amount of or significant amount of supraharmonics. But it has been observed that many DC fast chargers actually inject a significant amount of supraharmonics. So this should be, while designing, this should be taken into account. Maybe in future many standards should consider, notice this, and give some limits for this frequency range also, right? Now if you have this component with significant amplitude in a weaker grid, this can lead to a higher distortion of the voltage, and this voltage distortion may further cause supraharmonic currents through many installations, many components and devices, and those devices may not be designed to handle these amounts of current in this frequency range. In a nutshell, that this frequency range should be given attention in the standards and when you are designing your DC fast chargers, because it may have a significant impact on your, on the power system or within the charging station. So in a conclusion, so fast charging stations will have significant power quality impacts right? Especially harmonic stability study you should do. You should look at voltage fluctuations and flicker it may cause, and also the supraharmonics. And obviously larger power level, as higher you go, you have to be more careful about its impacts. And currently not much study have been done focusing on the fast charging stations. So in my opinion, further studies are required in great detail to know its impact on the system, especially harmonic stability point of view and other aspects. Yeah, thank you.